covered yesterday. Then we can take few questions and then cover session 7 scheduled for today. And then try to respond to the rest of the questions. I think that way you can cover both session 6 and 7 today. To the participants, we have already shared all the documents with you. The recording will be shared with you only after the webinar, so most likely early next week. So please use the chat box to pose only questions related to the technical content of the webinar. For other questions, please send them to us by email. So once again, we invite you to focus on the technical content of the webinar, of the presentation. Having said that, I will give the floor to Diego. Diego, if you are connected, then I give you the floor. Yeah, you have to open your microphone. Okay.
Great.
Yeah, I can hear you.
Great. Thank you. Thank you. Good morning or good afternoon, all of you. Welcome again for the third day of this webinar. Today we will try to move a little faster in some of the areas, since we have, as Sabine mentioned, we have to cover the content from yesterday that we weren't able to show, and we have to cover the content for today, planned for today. I guess we will be able to do that. So I will start sharing my screen so we can start with the webinar. Just one reminder, again, based on what Sabine just mentioned, because we are a lot of participants and it's quite difficult to track comments and questions in the chat if we are combining technical question and administrative issues. So if you please mind just putting questions to the technical content, so it's easier for us to track and answer them during the webinar. I will then share my screen. Let me know when you are seeing the screen.
Yeah, I can see your screen, Diego.
Great. Thank you very much.
No problem.
Okay, so we ended yesterday just here with, after reviewing some cases of when to use the standard deviation or the standard error. We will keep some of these issues yet during this discussion today because there are a lot of similarities here. And we are going to see last session 5, was focused exclusively on national statistics, focusing on censuses and surveys. During this session, during session 6, we are going to deal with any other type of data we are using in our GHG inventories, empirical data, that may come from different sources, so different type of information we will use. So we will see how we can apply statistical analysis to assess the data and come up with good information on the data itself, the average, and the associated uncertainty, depending on the type of information we are having access to. So the statistical analysis may apply to any case. We are seeing here, we will review today 3 cases when we have direct measurements that are obtained, where we have information from publications, from studies, from papers, from technical or scientific literature, or when we are having some other information to which we can apply statistics from chambers of commerce, from some sectors, or things like similar to national statistics, but not coming from a national governmental agency. So for future reference, you may go to Volume 1, Chapter 3, Section 3.2.2.2 to find more details about each of the 3 components for this empirical data. So the idea here is to see how we can quantify uncertainties in the inventories using statistical analysis, an approach that it's applied systematically, and it requires 6 steps that if you apply it one by one, you will be able to assess and extract information to quantify the uncertainty for the parameters you are applying in the inventory. So the 6 steps are, first of all, when we have a set of data, independently of if they are coming from measurements, from data published in a report, in a chamber of commerce, in a paper, scientific paper, or wherever, when we have a series of data, we have to first compile and evaluate this data set. In general, when we are dealing with large volumes of data, it's quite difficult just looking at the numbers to make a good assessment. So one of the first things we naturally tend to do, and it's part of this approach, is put some graphics and use some visuals to help us understand the behavior of this data. So visualization of the data with different type of graphs, it's very useful to have a first understanding of the data we are using. Once we've done that, we may try to fit this data into some kind of probability density function. We want to understand if the data behaves symmetrical or asymmetrical, if they are widely distributed or concentrated, if the variability is high or low, if the values are positive, negative, or a mixture of all of them. So we are trying to identify the behavior, what type of probability density function may be representative for this type of information. And then we are in a position to start trying to put some figures and numbers and understand the uncertainty associated to this data. Then we go to we do a probabilistic analysis, and we get all the probabilistic statistical figures: the average, the mean, the median, the mode, the standard deviation, the percentiles, all the descriptive statistics for the data. And we may, and it's not necessary, but it's a very good practice and very useful to perform a sensitivity analysis of the data once we arrive to the values for the associated uncertainty it may bring, particularly trying to understand the impact of this uncertainty, of the uncertainty in this data, into the total uncertainty of the inventory. So we will move to each of these steps. We will make a few examples to help us understand how to apply this approach. So the first two components, it's compilation, assessment, and visualization. We may try to create first, if it's a data series, we can just plot the data series and see how they behave. The trend, if it's stable, it's upward, downwards, if it's very variable, if it's stable. So plotting the data just that we receive will give us a first impression of the behavior of this information. We can check consistency. We can check if the series behaves properly. We can identify outliers if we see any. Because outliers may introduce some noise in the assessment of the uncertainty that may not really represent the real uncertainty of a parameter. So if we identify some outliers, it's good practice to test the uncertainty with and without the outliers and see what the difference in both assessments, what's the difference, and decide if we have to remove the outliers or not. We may use Pareto graphs, like plotting from the highest to the lowest and accumulating and see how they create the cumulative curve of data. We can plot histograms, very, very useful to understand if the data is similar to a normal distribution, if it's skewed, if it's symmetric or asymmetric, the width of the intervals. So different type of plotting that tells us and gives us a lot of information to further assess the information we are using. So let's move to number three. Number three stage is trying to select a potential probability density function to this data. So once we've seen the data with different graphs, we are able to initially identify some candidates for probability density function. We may see that the data is quite symmetrical. So the most probable selection would be a normal distribution. We may see some asymmetry in the data. So we may try to identify if a log normal distribution may be a good fit or any other candidate, if the values are all positive or if there are negative values. So we have to identify the characteristics of the data to try to select some candidates for probability density functions based on the shape, the size, how they behave, based on the understanding of the physical process, because there are some processes that naturally yields to some type of probability density function. Typically, multiplicative processes tend to be log normal distributed. Addition process tends to normal distribution as the central limit theorem. So the physical process behind the data, it's very important to select the potential probability density function, ask for expert opinion, the ones that are working in the sector, ask them and provide feedback on what are the potential distributions that this data may fit to, see the variability. And of course, if we are using some more sophisticated softwares, we can run goodness of fit tests. There are a lot of tests, statistical tests, that you can run on a set of data that will tell you which probability density function best fits this data. So if we are using some softwares, we can just select the data and run a goodness of fit test, and we will have a ranking of different probability density function that may fit this data. So once we've done that and we select one probability density function, we can have an assessment of the uncertainty in the mean of the distributions. Then we input this probabilistic analysis into the uncertainty of the emissions, and based on that, we may run a sensitivity analysis to assess the implications in the result due to the variability or the uncertainty in the input data. And this, again, I will repeat it until Friday, because this part is one of the most important outcomes of the uncertainty assessment, to use this to prioritize efforts to improve data continuously after each cycle of inventory development. So we have to decide if we are defining the uncertainty based on the standard deviation, the sigma. Let me see the pointer. Based on the sigma, the standard deviation, or based on the standard error, if we are applying an average value to a whole population, the standard error may be more appropriate. If we are applying an average value to one application or to one component of the total population, then the standard deviation may be more appropriate. So we have to decide which one we will use to quantify the uncertainty. Then we quantify the confidence interval, the 95% confidence interval for the uncertainty of the variable. We put this in the model and we propagate the uncertainty into the total emissions. We will see how to do that after this session and tomorrow. And then we match and understand how the total uncertainty relates to the input variable we are including. So this is kind of the general overview of the procedure we are that it's good practice to apply when we do statistical analysis to a set of data that we want to assess the uncertainty. Let's now try to put some fingers in action, and we will work on the Excel you received. There is a sheet in the Excel. It's related to the it's a case for industrial production, industrial processes and product use, in particular for the sector of aluminum production. And it's related to measurements where we have information, we have data on the anode effect. Don't worry about if you don't know the anode effect. It's some process when producing aluminum. There is some in the electrodes. There are some effects that create GHG emissions. It depends on the voltage, the current. It's some undesired effect. So it creates some emissions, fluorinated emissions. And we have data measurements from a plant, aluminum production plant, and we want to run a statistical analysis to assess this data and come up with a value to be used and the associated uncertainty. So I will switch to the Excel. Let me just share the screen with the Excel. You may all access your Excel. Are you seeing the Excel file, or are you seeing
You go.
You can see the Excel? Great. Okay.
Could you please make it a bit wider, Diego?
Yes, I'm just zooming. Is that okay?
Wait, okay, good, thank you.
You're welcome. So we have here a set of data, measurement from an aluminum production plant. It's related to the emission factor for CF4, related to the production of aluminum. And we have monthly data measured at the plant for 2 years, from January 2014 to December 2016. And based on this, we need to come up with a value that is representative of the production process and the associated uncertainty. So this is the data, the raw data we have, and we have to run the statistical analysis. So we mentioned that the first step is to plot the data. So if we just select, we insert, I will just insert a chart, select the data. Okay. So for instance, we can just see how this information, how this data behave. We see the variability of the data here in this type of charts. We see the variability. We see the trend. It seems to have a quite stable trend. We don't see an upward or downward trend. So it seems that we could use just an average for several years that could be applicable for the years to come. That's quite good. So we could, at first, it seems we could use some kind of average representing the behavior for different years. So another thing we could do is to create another plot. We could see, for instance, we can insert some Pareto chart. Title. I will just change a little the axis here. I will make it even. So if we plot a histogram for this data, we start seeing some kind of probability density function. We see, at least with this data, with this information, it seems to be some asymmetry of the data. It seems to have some more concentrated values near lower factors. We can play here a little with the axis. For instance, we may change the number of bins. We can increase it to see how it behaves. We still see some concentration to lower values, but not so big. So I increased again the number of bins. The bins, it's how many bars we see in the plot. So we just play around a little with the graph of the figures until we kind of better understand the behavior of the data. So to me, when I see this, I kind of think that it seems to have some asymmetry, but not so big. So it could be a normal distribution. It could be assimilated to a normal distribution, or if I want to be more precise, I could try to use a log normal distribution, but with not so skewed, not very asymmetric. So we've run the visualization of the data. So after this, we decided that perhaps a normal distribution or a log normal distribution may be a good fit. Of course, we can calculate all the parameters by our own. We can calculate the mean. Let's use average here. We can calculate the average. We can calculate the median. The median is the point here in this distribution, is the place where we have 50% of the cases to the left and 50% of the cases to the right. That's the median. That in a normal distribution is exactly the same as the mean, the average. So let's calculate the median. See how they differ from the average. Sorry. I hope you are all following the Excel. I know it's difficult to play your own Excel and at the same time watch at the screen of what I'm doing. So I hope you managed to do both things. So here, just we see that the typical average it's a little higher than the median. That shows that there are some asymmetry, the data, but it's not so big. We can also, let me move this down. We can also include here the geometric mean that we talked about yesterday. So geometric mean. For the same data, and we see the geometric mean. It's similar to the arithmetic mean, to the average. The average, the typical average is, adding all the numbers and dividing by the number of values we have. The geometric mean, it's multiplying all the numbers and doing a routing and routing those multiplications. So if we had 3 numbers, we would calculate the third root of the multiplication of the 3 values. So that's the definition of the geometric mean. So instead of adding and dividing by the number, you multiply and calculate the nth root of the result. So we see the numbers, the mean, the median, the geometric mean. We can calculate the mode if we have. I don't think we have the mode here because it's a finite number. But the mode is the most repeated value in a series of values. I don't think we have repeating numbers here, so we may not have a mode. But we have just a lot of information here. We can calculate the standard deviation. Can calculate the standard deviation of the whole series. And we match the standard deviation. We can calculate the standard error as the standard deviation divided by the square root of the number of values we have. In this case, it's 36. It's 3 years data, 12 months each year, 36 data points. So the standard error, we can calculate the coefficient between the standard deviation and the mean. That's a variability of 22%. The standard deviation represents a variability of 22% related to the mean value. The standard error represents around 4% variability, 3.6% variability. This is a standard error related to the mean. So we have a lot of numbers here. And let's go back to the first step. We had the data. We plot some data to understand the variability, the consistency, the trend. We plot the data into a histogram to understand the symmetry, the width of the values. We calculated some parameters from the statistics, descriptive statistic, the mean, the median, the geometric mean, the standard deviation, the standard error, the relations between the standard deviation and the standard error related to the means. So we have a lot of different values here. Just for your information, depending on the version of Excel you have, there is a very interesting function that simplifies a lot these calculations. That's run, if you go try to do it yourself in your Excels, try to go to Data tab, and you may have an option called Data Analysis. If you don't have this Data Analysis tab, you may need to activate it from the, like you can go to File here. You can go to File. You can go down to Options. And under Options, you go to Add-ins near the bottom. And Manage Excel Add-ins. So you go there and you have some options to select here. Again, depending on the version of Excel you have. So if you don't have this activated analysis toolpack, you can activate it. And then you will be able to find this option here, data analysis. So you may use just the option of, you have a lot of options here to do some statistical analysis for a lot of different cases. But the one we are interested here today is the descriptive statistics. We can run the descriptive statistics. We tell the range we are using. This is the data for which we want the descriptive statistics. We can select where to see this data. We may ask for summary statistics, confidence interval level for the mean. We can set it at 90%, 95%, whatever. So we are using 95% in the IPCC guidelines for the uncertainty assessment. So we have 95% confidence interval level for the mean. And we will just see a table with all the descriptive statistics, the mean. You can see that these values are the same that the ones we calculated. The mean, we will just copy and paste these values next to the table just for you to easily track that they are the same. So the mean, it's the same. The median, it's the same. The standard deviation, it's the same. Well, that's all. We also calculated the geometric mean. But you have here all the descriptive statistics related to this data. I will go just for a moment to the chat in case there is some comment. I see a lot of comments here. Okay, I still see a lot of questions related to administrative issues. if we have a linear trend in the data, do we need to detrend the data? That depends on what you are using the data for. If you see a trend, an upward trend or a downward trend, that may mean that you may require to update the emission factor. In this case, for example, in this case in particular, we are dealing to understanding the emission factor for the production of aluminium. And we see it's quite stable, so we may use some emission factor for different years. But if we see a trend, that means that we may need to update the emission factor for different years according to the trend, upwards or downwards, to really reflect the situation in that year in particular. Which we found some special patterns of the data, for example, multi-peak pattern, etc. Well, there are a lot. Statistical analysis it's a world itself. There are a lot of tests that could be done. If we see that there are some multiple peaks, we may be in the presence of multimodal distributions. So one probable solution or one thing that may be happening is that we are combining two different populations into one. So we are seeing two peaks, but in reality, they are two normal distributions that are combined. So that's why we see two peaks there or something like that. So if we see some things weird, some things that seems not to match a probability density function, a PDF, we may need to dig further, deeper into the data set to identify if we are mixing something and if we could make some separation or stratify the data, because perhaps it may depend on the season, it may depend on the production process in particular, it may depend on the raw materials. We need to identify the drivers and see if we can have more understandable data from the same data we are using. And we need to investigate further to see how to deal with it, what to do. Can you please repeat the interpretation of values calculated in the last two rows? I think if you are referring to we calculated the average, the mean, the median, which is the point that leaves 50% probability to the left and 50% probability to the right. We calculated the standard deviation, the standard error, and the ratios, the coefficient of variation, the ratio between the standard deviation and the mean, and the ratio between the standard error and the mean. Those are relative values, percentages, how much the standard deviation or the standard error varies from in relation to the mean. See a few questions related to the statistics results, the script of function. How to interpret the confidence level obtained and how it's related to uncertainty. The confidence level, I will go back to the Excel. This, yes, you are referring here to the confidence level. This is the confidence level for the mean at the 95 percentage. So this is how many times, this is an absolute value. This has units. It's the same units as the data. It's grams of CF4 per ton of aluminium. This is the standard error. This is the standard error multiplied by the key statistic, the student key statistics that yields the 95% confidence interval. You can calculate it by your own if you just multiply the standard error by the key statistics, which you can calculate it directly in Excel. I think it was the inverse or something. This T inverse. It's the t-test for two-tail, and I want a probability of 95, or in reality a probability of 5%, like just the 5% tail, and the degrees of freedom is the number we have here. I think it's the degrees of freedom is the number -1. There you go. So you see, these are the same values. This confidence level means that you have to move. I will just, let me copy and paste this to show you the t-value. If you remember, we've been talking about a t-value of 1.96. That means if you move 1.96 times to the left or to the right from the mean, you will have the 95% confidence interval. This 1.96, it's true for infinite sample. So in the limit, that's the true value. When we have a limited number of values, in this case 36, we need to factor in that. This is a smaller number. So the degrees of freedom, that's called the degrees of freedom for the t-test, for the t-distribution. And when we do that, instead of 1.96, we should apply 2.03. So it's almost the same in reality. It's around 2 times each side of the mean gives you the 95% confidence interval. That means that if you, and we are just approaching the end of this, on how to derive the uncertainty, then that means if we can calculate the lower limit and the upper limit of the confidence interval by subtracting to the mean this confidence level. And we will have the upper limit by adding to the mean this confidence level. And now we are ready to express the uncertainty, because we have the mean value (64.3), and we have the lower limit and the upper limit. So what's the uncertainty for this value? Well, since you need to move 4.68 to each side when you make it reference to the mean in relative terms, that means that the uncertainty for this parameter, this is the parameter we will use, the emission factor, for instance, 64.3, the uncertainty associated to this parameter is 7%. That's the result of this statistical analysis based on data we had. You see? I go back to the chat just for a few seconds. Okay, can you show again how you calculate the standard error? Can you clarify why do we have a lower percentage for standard error over the mean versus standard deviation over the mean? Here we have an Excel with data only. Yes, that's the idea. You also, because in the real life, you will have the data only and you will have to perform the statistical analysis of the data, but I can share after the webinar the data with the assessment already included in the Excel. Sure. So one question was why was this difference. One, the variability of the data, the standard deviation divided by the mean. This is the variability of the data, 22%. And the standard error related to the mean, it's a lot smaller. It's around 3.6%, 4% approximately. That means that if we are using the mean value, the variability of the mean is much lower because this 22% is the variability of the data. But if we are applying the mean to the sector, the variability of the mean is much lower, and that's the uncertainty we are interested in. You could do the exercise, for instance, if you calculate the annual average, for instance, what happened if I calculate here the average for each year in particular. $62.5 for year 15, 67 for year 16, 62. Now, if I take the average here, the average of the averages of course, it's the same, but if I calculate the standard deviation of this, standard deviation of the averages values, you will see it's pretty similar to the standard error. That's the idea of the standard error. The standard error represents the variability of the average values. See? So the variability of the average value it's much lower than the variability of each individual data. So that's why this is much lower than this other value. But bottom line of this, we ended up assessing the data, getting the values, and getting the uncertainty of the values. Is there any practical interpretation of the standard error over the mean? Yes, that's the variability of the average. That's how much the average varies in a sample. The variability of the average, it's the precision of the average, it's the uncertainty associated to the average. That's the interpretation. When we just apply standard error divided by the mean, we are assuming implicitly a t factor, the t-test of 1, which means that if we create a confidence interval adding and subtracting one standard error, we will reach a confidence interval of, if I don't remember wrongly, around 66%. If we move 2 times standard error each side of the mean, we will have a confidence interval of around 95% confidence, and that's what we are using in the IPCC guidelines. Okay, so I will go back, stop sharing Excel, and we'll go back to the presentation. So after this, what we have was that we were able to plot the data, calculate the average, the standard deviation, the standard error, and the associated uncertainty. One important thing here is when we are dealing with measurements, when we have data coming from measurements, we need to be very careful what these measurements were done, why they were done for. Because it may be the case that if measurements were done for other purposes than GHG emissions, which is most of the case, the reality, we just use existing data. It's very, very difficult that we have some statistics specifically designed for GHG inventories, particularly in developing countries. So we make use of any statistics we can find just to complete the emission sources calculation. So if we use information from measurements that we're taking for other purposes, we may need to check some bias because measurement could be done for some other reasons, particularly for some methane measurements done for safety purposes or things like that, that results are higher because they are measured when methane was high or something like that. So we should take those measurements carefully and assess the representativeness of that data. So with that, we end session that was pending yesterday. And we will move quickly to today's topic that is related to how to combine uncertainties. And I will pause 2 minutes here just to understand where we are. We have on Monday a first session that levels the ground, trying to understand the approach for uncertainty, trying to understand the notation, the terminology we are using, and understanding the sources of uncertainty. Yesterday and the first part of today, we dealt with how to get the uncertainty for each individual values we are using and applying to the GHG inventories. From now on, for the rest of today and tomorrow, we will now see how to combine these uncertainties and see how these individual uncertainties impact the result of the inventory. And we will see how to calculate the uncertainty of the national GHG inventory. That's what we want to know. We want to know the uncertainty of the result. And to do that, we need to know the uncertainty of the input data, and we need to know how to combine those uncertainties, reach to the uncertainty of the results. So today, we will go through approach 1, propagation of errors. We will understand the basics of the technique and the assumptions. We will learn how to apply it to several cases, how to identify key variables and avoid some common pitfalls in applying this approach. And we will learn how to deal with some asymmetric cases if we have, or if we prefer to move a step forward and take into consideration those cases that are not symmetric. Okay, we will see some techniques to do that. The first thing we need to understand is what's error propagation. What is linear error propagation? That's the technique we will apply. And the idea is basically that if we have any function, in the case of the GHG inventory, it may be the multiplication of the activity data and the emission factor, or the addition of several emissions from different sources. Whichever the function we have, the linear error propagation theory says that we will propagate the input data into the output based not on the function in particular, but based on a linearization of the function. So we will propagate the uncertainty. Imagine this is one variable. If we have an uncertainty in X, we will propagate this uncertainty according to the black dotted lines. The reality is that we should propagate it based on the function we are using, following the red lines. Well, the linear error theory says we will simplify this and propagate it linearly. So we assume the propagation is linear in this case. So that's one of the first assumptions, and it's very important because that depends if we have a very nonlinear function and we are assuming a linear propagation, we are introducing some error that it's due to the assumption behind the model we are using. And the assumptions under this model is that we are assuming that this variation, the uncertainty, it's quite small. It's quite small. It's around 30%. Small variations. The longer, the higher the variation, it may start to fail. These assumptions, the linear error propagation theory may start to fail. We assume symmetric distributions and normal distributions in particular. So we assume the uncertainty in the input data is symmetrical, and we assume that the output is also symmetrical. Those are assumptions of this model, of this theory. We also assume that the variables we are combining are independent, are uncorrelated, and we, at least in the IPCC guidelines, we are only provided equations for multiplications or additions. Any other function, we don't have an equation to propagate the uncertainty. So that's the model. And it's based, don't worry if you don't remember, I don't expect you to remember. If you do remember Taylor series expansion, that's great. You will take a lot of advantage and understand a lot of things much better. But if you don't worry, you just need to understand the assumptions to apply it, that the Taylor series expansion is it's an approximation of any function that depends on the derivatives. The first derivative, the second derivative, the third derivative, it's the series, it's infinite. Well, the linear error propagation only considers the first derivative. That's why it's linear. It's just the slope of the function in the point of estimate. It just uses the first derivative and ignores the higher terms in the subsequent derivatives. That's the assumption of the model. And with these two conditions for multiplication and addition, we have equations 3.1 and 3.2 in the IPCC guidelines. So let's dig a little deeper into this model, just to better understand the restrictions, because we can apply it as it is without thinking of anything else. And in most of the cases, it will work well. But it's important to understand that there are some cases and some situations that the model is not ready to deal with. It's not appropriate to deal with some situations that are outside the assumptions in the model. So I want you to clearly understand why those assumptions are in place, so you can understand when it may be a good estimate and when it may fail. So we'll go through some quick theory behind this model. Don't panic, just don't pay attention if you don't like math, if you don't remember anything about Taylor expansion. Don't pay attention to the equations in particular, just listen to the rationale behind those. And if you do like math and things like that, you may follow the equations and you may find it very clarifying of why those assumptions are there. So the first thing is the model, as I mentioned, is based on the Taylor expansion, just using the first order. So in theory, the function should be an infinite addition of several terms with different derivatives, higher order, but we are just using the first one, the first derivative. So we are ignoring all the rest. So if we calculate the difference between the approximation and the real value, we just move this term to the other side of the equation. What we have is just the delta. We have the delta, the difference in the result, depending on the delta of the input data. So that's the origin of the model. We can understand how the result varies depending on the variation on the input data. In this case, it's two variables, A and B. That yields this first assumption, that we need small deviations, because the Taylor series expansion works well when we are in an interval that it's close to the point of estimate. If we move a lot from the point of estimate, the approximation may not be good. So that's why we have this first assumption that we need small variations. Then when we add the statistic part of this, here we have the equation that links the variation in the input data with the variation in the results. So when we add the statistic part here and we want to calculate the variance of the result, and we apply here the variance of estimation of two terms that we have here. We have two terms here that are added all together. So the variance of a sum is the sum of the variances plus 2 times a term that it's related to this, that it's the covariance. It's how the two variables A and B are correlated. They may be correlated or they may not be correlated. So that yields to the second assumption that it needs to be symmetric and normal distributed, because we are applying the variance concept and the standard distribution, the normal distribution, to assign these variabilities. So let's apply this formula to the case where we have a multiplication. That's the typical case where we have activity data and emission factors. And we have activity data and emission factors, and we apply this first derivative and the squares, we obtain something like this. This first part, the first derivative, this second part, the first derivative of the other variable, and the correlation between the variables A and B. That we are propagating, we are using uncertainty in relative terms, in percentages. So if we divide it by the function, by the value we are using to make it relative, you can see those, and we divide by A times B, which is the function here. You can see that the red parameters cancel each other. So we end up with the relative uncertainty of variable A squared, or in our terms, the variance of parameter A plus the variance of parameter B, or the standard deviation square. So if we calculate just the uncertainty of the function, we have to square root this. And that's equation 3.1 of IPCC guidelines. That's what we are given just as the equation in IPCC guidelines. I will move quickly to the chat. I see a lot of comments here. Okay, perhaps then if you can help me identify some of the questions there that may be relevant to this part, or if there are similar, so we can address several with one. That would be helpful. If not, I can just scroll to some of them. I see one. Can you explain why equation 3.1 and 3.2 do not apply for division and subtraction? We will reach there in a few slides. It's not that they don't apply. It applies to subtraction. It's the same as the addition. We will review a few cases, a few examples for this parameter. I see a table with data there. I'm not sure what that means. From sensitivity analysis. Okay, that would be very similar to what we just did with the aluminum emission factor. You need more detail or specific guidance with one particular case. We can take it offline through email after the webinar. For the calculation, there were many formulas and details, but I'm still not sure about their importance or how should we use those values. I guess you are referring to these formulas for deriving the equations shown in the IPCC. If that's the question, you don't really need to understand the formulas. I just wanted you to understand why the assumptions are there, the rationale of each of the assumptions there. If you want to understand the formula, if you like it and you want, it will be very useful for you in future inventories, because if you face some function that it's not either a multiplication or an addition, you may apply the formula directly and derive the correct equation to be applied. We will see some examples here. And this method to determine the uncertainty of emission factor in a country bill based on several parameters, for instance, the emission factor of methane in tank fermentation, not from measurement. If you are referring to the statistical analysis, yes, you can do a statistical analysis from different data you have and create a country applicable emission factor. It could be from measurements, it could be from literature, from papers published in the country in different regions. The importance is to make sure that the values you are using is representative for the situation in the whole country and not biased for some regions or some specific activities, disregarding others that may not be covered by that information. So again, I see a response from Gabriel Molina answering the applicability of equations to subtractions. Thank you very much, Gabriel. So let's move now to a few cases then. So with these equations we have are applicable for multiplication or additions. Of course, subtractions are additions with negative numbers, so it applies the same. But if we don't have a multiplication or addition, we could always go back to this formula. That's the general one, and apply it to any function. If we can get the first derivative of the function, we can apply the formula. The last assumption, the correlated values, comes from the issue that this equation, if we ignore correlation, if we assume the variables are independent, are correlated, we can ignore this term and keep these two active, and that's what equation 3.1 does. So equation 3.1 assumes uncorrelated variables. If we know there are some correlation, we may include this part 2 times the covariation, the combined the combined standard deviation, so the covariance of the data. If we know data is correlated, it's highly correlated, we may include this. That's outside the equations of IPCC, but that doesn't mean it's wrong. On the contrary, it's perfect that if you know there are some correlation, that you include this term if you want to take care of this correlation in your assessment. So let's see here a few examples of the importance of the variability of the data and the importance of the functions. You could see that in reality, the uncertainty in the data itself, it's not the only thing that it's important, because since we are propagating this uncertainty based using this linear error propagation theory, the propagation depends on the slope of the function in that estimate, in that point of estimate. So you may have the same uncertainty in the input parameter that results in completely different propagation results as the output. As you can see in the first figure or the second figure, both have the same input uncertainty, but the resulting uncertainty, the uncertainty of the output, is completely different. Or you can have a variable with a large uncertainty individual that, when it's propagated in the model, yields a very low uncertainty. That's why I've mentioned, I think, like 10 times the importance of the sensitivity analysis in this case, because it's very important to understand the uncertainty of the data you are using, but it's much important to understand how this uncertainty affects the uncertainty of the result. Because if we are in a case like this, we really don't care, and we don't want, and it wouldn't be efficient to assign resources to reduce the uncertainty of this parameter, because the impact of this uncertainty in the result is very small, it's negligible. So even if we put a lot of effort here and reduce the uncertainty to 10% of the original one, the result will hardly see this huge effort. So you don't need to spend resources here, but you will definitely would like to expend time, money, better data. In this case, where the impact in the result is significant, the uncertainty, the input value in the input data significantly affects the uncertainty of the result. So those are the cases we want to identify. And those are the cases we will assign resources in the next cycle of the inventory to improve the data we are using. So now we've seen where these variables, where these two equations came from. We've seen how this equation was derived. We didn't do the same for the addition, but it's the same approach. But ultimately, we have the two equations for cases where we have multiplicative processes and for cases where we have additions. Let's try now a few cases. Let's apply these equations to different cases. You have the Excel file with the cases in one of the sheets, linear error propagation. I will not share the Excel because the data is already included in the presentation, so you may follow the presentation. And if you want, you can also look at your particular Excel to follow the equations, in particular within the cell. Let's apply to the first very, very easy case. Typical case where we have, for instance, in energy sector, we have a fuel consumption and the emission factor for that fuel. And we calculate the emissions as the consumption times the emission factor. We have the gas oil consumption, for instance, some expressed in energy units. And imagine we go to IPCC, we find the full values for the emission factors for gas oil, and we have these parameters. So The first thing we have to do, naturally, what we have been doing until now, it's calculating the emissions. We calculate the consumption times the emission factor, and we have the resulting emissions. Then we assess the uncertainty of the data, the gas oil consumption. We reach the energy agency from which we extracted this data, and we arrive to the conclusion that the uncertainty for the data is around 10%. That's just the example. You should do that and assess the uncertainty in particular for your case. In your country, the type of data you're using, you should obtain this type of information. Ultimately, you have some guidance in IPCC guidelines related to the level of uncertainty that may be expected for different countries, depending on the statistics, if they are good statistics, some intermediate, poor statistics. Depending on that, you have some guidance to extract this information. So what we have to do is now understand the uncertainty of the emission factor. So we have the lower limit, the upper limit, and the default value. So we can calculate the uncertainty as we did on Monday. From the two sides, we see one, it's around 2%, the other, it's around 1%. I will not spend a lot of time here because we've already gone through this. So we may end up saying that the uncertainty associated to the emission factor here, 2%. So we have all the data for the uncertainty in the input data. Let's apply now the formula. So the formula tells us that we have to square the uncertainties, add all the squares, and calculate the square root. So 10% square, 2% square, and then the square root of the result. If you do that calculation, that gives 10.2% approximately. That's around 10%. Again, we don't need, and it's not good practice to use a lot of digits to express uncertainty because we are using estimates. It makes no sense. If the uncertainty is around 10%, it makes no sense at all to say that it's 10.2 because we really don't know if this data, 10% of this data is around 139 rounded. So it makes no sense to factor in the 0.2 and include some decimals here because we are already uncertain if this 3 is 3 or is 4 when we add 1 or is 2 if we subtract 1. So it makes no sense to factor in the 0.2 in the uncertainty. It makes no sense at all. So we are very happy to understand that the uncertainty is around 10% for this calculation. That's good enough. So that's a basic assumption. Just in case you ask yourself, I've used 10% here, 10. It's the same, exactly the same if you use 0.1 and 0.002 representing the 2%. So it's exactly the same result. So you yield to 10% uncertainty, either expressed as percentages or expressed as fractions. That's exactly the same. It's your choice which one you feel more comfortable with. So let's apply to another case. Now we have several parameters that are multiplied all together. I see a question there, if the uncertainty emission factor have a larger difference in the lower and the upper limit. Let's say minus 2% plus 36%. Which one would we use in the approach one method to combine the higher value That's a very good question. We will touch something around asymmetric uncertainty and how to deal with this in the model. The model assumes symmetry, assumes normal distributions, and assumes that the uncertainty is symmetric. So if we have asymmetric cases, in theory, the model is not prepared to deal with that. So we have to select one value to apply to the model. We could select the higher value, 36 in this case. That creates the problem that you have the left-hand tail much longer than you should be. But on the other side, if you just select 2%, it's not really representative of the real uncertainty. So you have to make a choice there. You have to put an assumption there and select one variable. My suggestion, in my experience, what works best is to use something in between. Not the lower, not the upper, something in between that kind of reflects the variability, keeping the 95 confidence interval. Of course, it would be moved a little because we are assigning a symmetric interval when the reality is asymmetric. So you have to compromise something. But I've seen good results using something in between the two values. Let's move. I have a few cases. Divisions are one of the cases we are dealing with. So let's just wait for a few slides to deal with divisions and subtraction and those kind of things. Let's follow and concentrate on the ones we are seeing here. Now we are keeping the multiplication, but we have several data here. So we will do something similar. We have data for the emission factor here. We have data for the net calorific value here. We have the uncertainties there. We have the gasoil, the consumption, the fuel consumption. We have the density of the fuel because it's expressed in cubic meters, and we will need to transform it to mass units. We derive the uncertainty somehow, as we've seen the first part of today and yesterday and Monday. We obtain the data on uncertainty for the activity data, for the density, the consumption. We do the calculation, and we reach the emissions. Now, we want to propagate these individual uncertainties that we've decided to apply the uncertainty for the emission factors, the default emission factors in IPCC. This is one case that can be assimilated to asymmetric case where we have a lower uncertainty of 4% and an upper uncertainty of 1%. That's quite asymmetric. I just applied the higher value here, the 4%. It's more conservative if you wish, but it's not my best choice. In reality, I would use something in between, something around 2-3%. In this case, it doesn't make much of a problem because the uncertainties yet are small. So the result, and it's a very simple equation, so the result will not change much if we use one or another. Moreover, when we compare that, we have 5% uncertainty in each of the other parameters. So when we apply the formula here, we just do the same approach. Each of the individual uncertainties, we square all of them, the two 5%, the 2%, and the 4%, and we calculate the square root. That gives us an uncertainty of around 8%. So that's the associated uncertainty to the emissions due to combustion of fuels, of, in this case, gas oil. I took the density uncertainty from somewhere. In this case, it's just an example, but in reality, you should, if you are using gas oil in your country, you should try to get the uncertainty, the data for the density of the gas oil that is distributed and sold in your country, get the specifications of that gas oil, and if possible, apply the emission factor for that fuel in particular and the density. In general, fuel companies have the specifications of the densities of the fuel they are providing, and in general, they have ranges to comply with. According to the law, there are some specifications they have to comply with, so you may easily find these specifications for the country, and you have the interval of the density that may contain for that a fuel may be required to comply with, and there you have the tools to derive the uncertainty data. What if the density uncertainty isn't known? Can we proceed without it? If you proceed without it, you are assuming that the density has no uncertainty, and that's not true. You can ignore it, but you will be underestimating the uncertainty of the result. If you know that the uncertainty is small, it may be okay if you just ignore it, or if you may assign just a small uncertainty to the input data and include it. The result will not change much. But if you may be dealing with some fuels with higher density variations, it's better you explore a little more on the data to get proper information. So let's skip a few other cases, because we've seen two cases that are very traditional, just multiplications. Let's see how to apply it to some other cases that are not strictly multiplications. For instance, there are some emission sources, some categories where the emissions, the formulas, the equations we are using contain some equations that are not multiplication. For instance, squares or something like that. That's the case, for instance, in enteric fermentation with the digestibility and things like that. You can find there are some squares in the equations. So in theory, we don't have an equation to deal with squares. However, we all easily understand that squares, it's just the multiplication of the same parameter 2 times. If we have a factor 3 here, it's just multiplying 3 times the same value. So in reality, we can apply the equation 3.1, just propagate this uncertainty, but multiplying 3 times with 3 factors. So where the uncertainty for, in this case, this digestibility, DE parameter, and it's not my name, Diego Escurra, it's digestibility, we have to factor the uncertainty of this parameter twice. That's it. We can just apply the same formula. So we apply the same formula, but factoring the uncertainty of these parameters 2 times. What happened to divisions? I've seen a question there related to divisions. Well, in theory, we don't have an equation for divisions, but in reality, we can apply this equation to divisions. Because divisions, again, it's similar to this case. Divided by a number, it's the same that multiplying, but the inverse of the number. So, for instance, that's very common in the transport sector. We may have cases where we need to divide by the efficiency of the vehicle. So we may, instead of dividing by the efficiency, we could multiply by the specific consumption, the specific fuel consumption, which is the same. It's the inverse of the efficiency. So in reality, we can also apply this formula that it's propagated. It's the sign for multiplication. And just apply the formula using the concept of multiplying by the inverse figure here. I see a comment there. Uncertain key in carbon salt in tropical forests are usually higher than 50%. Therefore, the assumption of small standard deviation is not met. How do we handle error propagation in this case? Well, you have two choices. You either apply it anyway, which is one of the recommendations in IPCC. If you have nothing else to do, you can just apply the model. You will get some results, but you need to understand that it may not be fully representative of that situation, and that will depend on the importance of that category in your inventory. If it's a very small category, it may have no impact at all. If it's a very important category, you may be encouraged to try to apply other approaches for that category. In particular, we will see on Friday, we will see the hybrid approach that combines approach 1 and approach 2. So for that case, the combined approach could be something you may explore. You have to wait until Friday. Why did we take only the lower 4 and 2 in the case 2 for emission factor and net calorific value? It just, if we have asymmetric, we have to make a selection. We have to select one. In this case, for the example, I just selected those. But for your case, you should assess which one or which value, if one, the other, or something in between, you should use. The two DEs, the digestibility, are not independent. That's a very good one. That's true. That's completely true. The two variables are not independent there. So if we factor the dependency there, you may need to include the values. In this case, since it's the product of the two variables, the problem is not that big because it's the same parameter, and correlation is 1 because they are fully correlated because they are the same parameter. So, but if you apply, for instance, the Monte Carlo approach that we will see tomorrow, the correlation of the parameter is not a problem because we will be applying a probability density function and factor that in already in the model. Let me see here. There are a few more. LULUCF in some cases we divide estimates between certain number of years to estimate rates. Can the linear propagation be used to calculate the uncertainty in various proxy data used for determining forest degradation? Yes, we will see on Friday how to apply proxy data and how to derive the uncertainty for the data when we are filling data gaps. For LULUCF2, we need to estimate the uncertainty of the division. When we are having divisions, we can also apply this formula. Of course, the impact, again, we can apply the formula without thinking a lot on the assumptions on when it's applicable or not, and you will reach a result that in most of the cases could be quite representative of the situation. However, it's important, again, for you to realize which are the categories that are important and which are the uncertainties in the input data that are important, so as to assess ex post if the result you are obtaining for applying this model makes sense or not for each of the individual categories. So it's not just one easy answer to those cases. You need to assess it case by case and understand the importance of the category, the level of the uncertainty in the input variables, how much you're complying with the assumptions or not, and what's the implications if you apply another approach. If you've never done uncertainty assessment, I suggest you just go to linear error propagation, apply it to all, and get the first result. And from that point onwards, you can start refining and assessing your data, but with some experience and some results already achieved. You may realize that some of the results are not appropriate. That's okay. It's your first exercise. So you can explore further alternatives to improve those results. If you've already done some uncertainty assessment and you're ready to move forward and go deeper and enhance your results, you can explore other approaches as multicolor simulation or applying this linear error propagation, but considering asymmetric cases, which we will see in a few minutes. So what happens when we have an equation, like typically in waste treatment, we have equations that are non-linear, are not powers, are not divisions, are not subtractions. So what happened there? We don't have an equation where we cannot apply those equations here. But if we go to the theory, we can calculate the first derivatives of this equation. If you would like to do that, that's very good. If you like math, you can do that. You can try it. It's quite simple if you like math. If you are if you are used to dealing with this type of calculations, so you can derive your own linear error propagation formula for any function you need. So most of the function would be multiplications or additions or a combination of those. But if they are not, you could also derive these equations. So in this case, for the exponential function, we can derive the equation. The first part is just the multiplication of two parameters. That's here, but the uncertainty of this part, you will see this is the result, and this is the formula you may use to propagate the uncertainty for the parameter, the composable degradable organic carbon. This is for waste treatment, and the K parameters related to the decay rate in a landfill or anything like that. So you have a formula and you have a way to derive this linear error propagation formula to any other function you would like to do that. So let's move now to the other equation, 3.2, that is applicable to additions. And of course, we will start with a very simple case. I will move a little faster now because we've gone through a lot right now. We want to add two emissions. We have the emissions, we calculate the result, we have the uncertainty of each of the emissions, that would be the input in this case, and we apply the formula. We just propagate the uncertainty as the uncertainty of the parameter multiplied by the value of the parameter. That's the first part. The uncertainty of the other parameter, 10%, multiplied by the parameter. We square that, we calculate the square root, and we make it relative, because when we multiply the uncertainty by the parameter, what we are having there is the delta, is the real value. It's not relative. It's this value, almost 3,000 and around 500. That's the result. So we make it relative by dividing by the result of the emissions. So we see the uncertainty of the result is 24%. I will remove a few lines just to make presentation not so messy. So that's how we apply this formula. What happens when we have several values that are added all together, which is very common case. It's the case of the entity. We add all the emission sources all together. So we have the emissions, we have the associated uncertainty to each of these emissions. We calculate the result, and we just apply the same formula, the uncertainty multiplied by the value. We square the results, we add all together, we calculate the square root, and we divide by the value. I think I see I have 1 0 here that shouldn't be there. That should be 1,900. So this gives a result of 13%. So that's how we propagate uncertainty in an addition. And of course, it works the same in subtraction, because subtraction is the addition of negative values. So there's no problem there. Since it's square, the negative part goes away. So the result is the same. But we will see how that works. One issue to understand here is that addition reduces the overall uncertainty. The longer the terms we are adding, the resulting uncertainty decreases according to the central limit theorem. So the uncertainty will decrease because the individual uncertainties start compensating each other. So the addition is a good thing. Addition reduces the overall uncertainty. But one further step we could take here regarding how much the impact we have for each of the individual sources into the result, we could calculate the contribution to the uncertainty of each of these parameters. So we can calculate how much this uncertainty affects the result. And we see, for instance, that the first source, emissions 1, that has a quite high uncertainty, 40%, not too high, but quite high. The contribution to the result is just 10%. The variable that has a larger contribution, there are 2 of them, around 40% of each of the contribution to the uncertainty of the results. For instance, in this case, this source, emissions 5, that has a low uncertainty, however, the contribution to the result is quite high. In this case, because the emissions are high, so we may care about this source because it's high and the contribution to the overall emissions is high. We see something similar with the contribution to variance. If you go to the spreadsheet that is attached to the IPCC guidelines on how to do the linear propagation or the IPCC model, you see a part that calculates the contribution to variance. So you can use that to assess this. Let's see how this applies to subtraction. When we subtract some variables, we do the same. It's exactly the same. I will not stop here much, but we just calculate the same if it were an addition because the negative parts are exactly the same. The only issue here that we should be very careful is that the uncertainty increases when we are subtracting values. You see, in these two examples, the data, the uncertainty in the input data is the same. It's exactly the same. However, in one case, we reach to an uncertainty of around 40%, and in this other case, we reach the uncertainty. U is the uncertainty, U the uncertainty. This uncertainty yields 170%, a huge uncertainty, because the two values, emissions 1 and emissions 2, are quite similar. So depending on how similar the values are, the uncertainty starts decreasing and it's not capped. So we should be very cautious when we are subtracting emissions that are similar in magnitude, because we may run in a problem of what it's called catastrophic cancellation. It was a very common and understood problem in math and numeric computation. It's called catastrophic cancellation because the uncertainty increases a lot when the two numbers that are being subtracted are similar. I see a few questions. Okay, there are several questions, and we are almost on time, so I may take those offline. We just move forward with a few slides that are yet to finish today. So the case where we apply the two equations combined, that's what we will do in our GHG inventories if we apply approach 1. Imagine we have something like this. We have the emission sources. We have here the emission sources, the value of the emissions, the uncertainty in the activity data, the uncertainty in the emission factors. We calculate the uncertainty of the results when we multiply activity data times emission factors by applying equation 3.1. That's what gives us this column, the results. And then we have to add all these emissions, and we propagate these emissions according to equation 2, where we calculate the value multiplied by the uncertainty square. That's this part of the equations. We do that for every single value. We can divide it by the sum of all the emissions, and we can square those just to make it consistent. We calculate this column, we add all the values, and then we square root this part. We square root all the summation, so we arrive to the uncertainty of the results. So that's how we apply linear error propagation here. We combine equations 1 when we have multiplications. We combine equations 3.2 when we have additions. So we are able to propagate all the individual uncertainties into the overall uncertainty of the results. And we can do that at any aggregate level of aggregation we want, for subcategories, for the whole inventory, for the main categories, energy, industrial, waste, agriculture, any single category. We can select the level of aggregation. We apply this approach. And just to finish, we are almost on time, but I would like just to show, this is the typical table I was mentioning before that you can apply, that it's very clear to apply. with all the sources, the input data, and how you propagate the emissions. And just a case that I think is very useful for those of you who have already experienced calculating uncertainty and want to incorporate asymmetric cases. One way to do that, because there are several ways, one way to do that is just to combine and propagate the uncertainties for the two sides separately. So imagine you have the emissions, you have the uncertainty in the activity data, and you have uncertainties for the lower limit and the upper limit. In some cases, there may be similar. In some cases, there may be large variations. So if you want to really deal with these asymmetric cases, what you could do is just to combine in the multiplicative processes separately the left side. So you combined 3 with 5 to reach this. And you can combine, sorry for the messy lines, 3 with the other limit to obtain the second one. So you apply it twice to the lower limit uncertainty and to the upper limit uncertainty. And then we combine those again by adding all of them. You combine the two separate, so you will end up with an asymmetric result of the emissions, telling you that the emissions may be 7% lower or 22% higher. That's one way of incorporating this kind of variability. Of course, that's not exact because we are applying a model that it's not designed for dealing with asymmetric cases, and we are applying it to an asymmetric case. So we are compromising some of the assumptions here, but we may have a first guess of how this asymmetry may impact the result. If we really want to take into consideration asymmetry, we may explore other approaches or move to approach 2, multicolor simulation, that we will see in more detail tomorrow. So I think that's all for me for today. Thank you very much for today, for being here a few minutes more than expected. And back to you, Sabine, for closing the session. Thank you very much.
Yeah, thank you, Diego, once again. So today we've learned how to apply statistical analysis to derive uncertainty associated with empirical data, and also how to combine uncertainty of input data, activity determination factors to derive uncertainty associated with each category, and then how to combine the uncertainty of all the categories to derive the uncertainty of the inventory totals. So we invite you to continue to practice. Like I mentioned at the beginning, we will share with you the spreadsheet used by Diego to do the calculation. We will share the file maybe early next week. We will also share the recordings. All the recordings will be shared with you together with that spreadsheet that I mentioned early next week. So once again, thank you. Tomorrow we will continue the webinar, and we will cover tomorrow the approach to combine uncertainty, which is the Monte Carlo simulation, which is an approach which is more sophisticated than the approach 1. So we strongly encourage you to join tomorrow at the same time, same link. So once again, Diego, thank you very much. And I also thank my colleagues from the Secretariat and those working on the interpretation. Thank you very much, and see you tomorrow. Bye-bye.